Okay, today we want to talk about another yield criterion called the Tresca yield criterion. Last time we looked at the von Mises yield criterion. Remember that was based on a pure J2 plasticity theory. So we sort of approached it from two different angles. One was saying that in the von Mises case that it relates to a octahedral shear stress, and then the other being that it relates to strain energy of the deviatoric strain, and both of those led us to a pure a J2 based yield function. So another yield surface type might just be to say, let's suppose that failure occurs whenever my maximum shear stress exceeds a critical value. So that's actually what the Tresca yield criterion is. It just simply states that yielding is going to occur when the maximum shear stress exceeds a critical value. So let's write that down. Okay, so the Tresca yield criterion what that gives us is it says that yielding occurs when the maximum shear stress, so when the max shear stress exceeds a critical value. Okay? And we'll just call that value K1. Okay? So we could write that as yielding occurs when tau max is equal to K1, or as we write the yield function kind of in a similar fashion to what we've done before, we might say that F is equal to tau max, the max shear stress squared, minus K1 squared. So when this quantity equals 0, then that's the yield surface. Okay, so now we just need to think through a little bit about how we could write tau max. So we could write this above alternatively. Let's see, alternatively we could write the following. We could say, okay, F, and now let's think about tau max in terms of Moore's circle. So if we're in the principal stress coordinate, then there are basically three circles in our Moore's circle diagram, and the halfway point, so to speak, between each of the principal stresses turns out to be the max shear stress in those planes. So we could call that, let's call that tau 1 squared. So there's three of these, right? Minus K1 squared times tau 2 squared minus K1 squared times tau 3 squared minus K1 squared. That quantity could give us our yield function as well, where we define tau 1, tau 1 being equal to 1/2, let's say sigma 1 we're in principal stress space, minus sigma 2. We would say tau 2 is equal to 1/2 sigma 2 minus sigma 3, and then tau 3 being 1/2 sigma 3 minus sigma 1. Okay? So based on Moore's circle, one of these must be tau max. So say based on Moore's circle, one must be tau max. Okay? So if you go back up in this equation here, what this says is that when this equals 0, it just means one of these factors must equal 0. So either tau 1, tau 2, or tau 3 is equal to tau max there. Okay? So let's think about then what it looks like if we were to plot the surface. So the Tresca failure surface plots as actually a hexagon in the pi plane. Okay, so the Tresca yield surface gives a hexagon in the pi plane. Okay? Remember, the pi plane is the octahedral plane that goes through the origin. Okay, so let's go ahead and try to draw that. There. Okay, so there's a hexagon in there. We would have these as our stress axes, sigma 1, sigma 2, sigma 3. We're looking down on the plane now. And so what we want to do is, so this is how it looks again as a in the pi plane. If you want to remember, the von Mises looked like a circle. So how does that look relative to the Tresca? So we need to define something and say that if the von Mises and Tresca, right? We have to decide where we want those criterion to agree at. But if we decide that they are going to agree in uniaxial tension, which is the convention, so if von Mises and Tresca agree in uniaxial tension, okay, right, that means that they're going to agree at these corners here, right? So then we could, let me draw with a different color here, right? Then the von Mises is going to agree at these 3 points. We can draw our ellipse, and it's going to look something like this. Going to meet at those points, something like that. Okay? So this curve, the red, is the von Mises. Of course, the black curve here is the Tresca. So, and let me just remind you that this agreement in uniaxial tension, that's by convention. It's not mandatory. Okay? That's not we didn't prove that or anything. And they're supposed to meet at the corners. I did my best to do that, but the idea being that you get this circle. The Tresca looks like it's inside the circle, and that is actually correct. Okay? So let's now talk a little bit about the properties of this Tresca criterion. Okay? So let's say the properties of the Tresca yield surface. Okay? Properties of the Tresca yield surface. Number one thing you should be able to see is that yielding is going to be the same whether I'm in tension or compression, right? So remember that this plane that we're looking at up here comes out at an angle towards us, and if we go back down the same way, that shape doesn't change. And so we could say that via isotropy, yielding is the same in compression or tension. So yielding is the same in compression or tension. Okay? And the same is true actually of the von Mises criteria, right? There's nothing special about going into compression versus tension. If there was, we'd need a different type of failure theory, like maybe something like what's called the Moore-Coulomb, which we might talk about later. Okay, so that's the first property that's important. The second property that's important is that because of isotropy, the yield surface here, again on this pi plane, these are all obviously, there's 6 components, so there's 60-degree increments. That the yield surface must be the same in each 60-degree sector. So say that because of isotropy, okay, the yield surface must be the same in each 60-degree sector. Okay? And again, that's also not anything different from the von Mises criteria. Of course, it has more symmetry than just that. It's completely symmetric. But in this case, because we're basically switching from, tau max can potentially jump from, looking at a principal stress between 1 and 2 to a principal stress between 2 and 3, etc. It has less symmetry than the von Mises, but still must be symmetric in that 60-degree sector. Okay? Number 3, this is sort of a larger one. Remember that our stability postulate said we had to have a convex yield surface. Okay? So the stability postulates that we talked about before, right? So stability postulates, they implied a convex yield surface. Okay? So what we can see from above, if we look at this plot, is that the Tresca surface is actually the inner bound on convexity. So the Tresca surface is equal to the inner bound on convexity. Okay? And to see that, just take this middle point here, right? Let's just locate this. Take that center point there. If we were to move it in, it flattens out. If we were to go beyond the Tresca, right? Take this von Mises curve and move it back beyond the Tresca. Now we have a concave surface. So we can see that, at least as this sits, the Tresca criteria represents the bound beyond which a failure surface can't cross and remain convex. Okay. We might also ask, what's the outer bound? So we can define an outer bound of convexity on convexity. Okay, and I'll draw that up here with a green. Okay, the outer bound on convexity looks something like it is also a hexagon, but it's now a hexagon that looks like this. I'm trying to make this a hexagon. Okay, so you kind of see what our limits are in terms of convexity. So this is the outer bound on convexity. Okay. And let's just think about why that would be. Well, if for example we were to bring these 2 points, so now this point and this point, if we were to bring them out beyond that surface, again, these points are fixed by some experimental data. If we were to bring these points out beyond that surface, we would then create a concavity there, which is why that represents our outer bound. Okay. Couple just features to note, that the max difference between the inner and outer bound on the convexity, so the max difference between the inner and outer bounds is approximately 25%. Okay? And we can also define the maximum error difference between the Tresca and von Mises, which is going to be obviously less than that. Between Tresca and von Mises is approximately 13.4%. Okay, that's the maximum difference. Okay, and then one final sort of comment here. So comment number 4. In the case of plane stress, we can write this biaxial surface like we've maybe seen in our machine design classes. So in the case of a plane stress, the biaxial surface is elliptical, or sort of elliptical. Okay, so let's go ahead and let's take the case where sigma 1 and sigma 2 are not equal to 0, and then sigma, that's still in principal stress space now, sigma 3 is equal to 0. So we can draw the sort of this biaxial envelope. So if this is sigma 1 and this is sigma 2, and let's say this goes 1, 2, 3, 4, 5. So let's say that's one failure point. If I pull on this one, I also go 1, 2, 3, 4, 5. Okay, something like that. And in the Tresca criterion, we actually get a straight line. Okay, I should draw this out the rest of the way as well. Okay, so 1, 2, 3, 4, 5. There it is. And then 1, 2, 3, 4, 5. Something here. Okay, so I should have made it a straighter line. So those cases all give straight lines. And what do these correspond to? Well, this corresponds to, this goes back to Mohr's circle again. This top flat line says that tau max is equal to 1/2 times what? Well, what's changing here is sigma 1, and we can see it doesn't change the tau max, so that the tau max must be only dependent on sigma 2 and then this sigma 3. So this is tau max is sigma 2 minus sigma 3. At this location, this line becomes tau max is equal to 1/2. Now it doesn't change with sigma 2, so this is sigma 1 minus sigma 3. Okay, and then this straight line here, now why is it changing? Why doesn't it have this nice square shape? Well, because now sigma 2 is negative, sigma 1 is positive, and so the tau max in this case is going to look like 1/2 times now sigma 1 minus sigma 2. Okay? We can also go ahead and plot in this case the von Mises failure envelope. Right, so the von Mises failure envelope gives us that ellipse that we hopefully remember, intersecting at these points. Okay, so the red is the von Mises, just for comparison. Okay, so hopefully that that describes sort of the Tresca criterion, how it differs from the von Mises, and how it's related to it as well. Okay, the last thing that I want to say sort of about the Tresca is that it's not properly a J2 yield criterion. So the Tresca is not a purely J2 criterion. Right, J2, remember, is the second invariant to the deviatoric stress tensor. So it's not purely a J2 yield criterion. Right, and the reason is that it incorporates something of J3. Okay, so it incorporates J3, where J3 was the determinant. If we're in principal stress space, we can write that determinant just as the principal deviatoric stresses multiplied together. Okay. So in that case, we would be able to then write that if we wanted to write the Tresca in terms of invariance, it actually is kind of a complicated equation, and we don't use this equation because it is complicated. But I want to show you that it's still related. This looks like 4J2 cubed minus 27 times J3 squared minus 36 times K1 squared times J2 squared plus 96 times K1 K1 to the 4th times J2, and then minus 64 times K1 to the 6th. Okay, so that's exciting. So the failure surface is of course defined when that equals 0, but you can see it's not purely J2. It has all these other components from J3 in there as well. And then the final thing I want to give you with respect to Tresca and von Mises is that experimentally, von Mises gives better agreement typically than Tresca. Okay, so probably why we often see von Mises being used. It's also smooth in contrast to Tresca, which has sharp edges. So there's a variety of reasons we would maybe choose Tresca. Okay, so but I at least want you to be aware of that because it is a prominent failure criterion that you need to be familiar with.